Alrighty guys, welcome back to the Biomechanics 1 video series. This particular lecture is looking at the introduction of torque and what it's all about. So torque by definition is the ability of a force to cause rotation. So there's two things that we already know. Force is a vector quantity, meaning that it has both magnitude and direction. So the size of the force and the direction in which the force tends to act will be really important when we talk about rotation. And the second factor is that we have rotation. Rotation typically requires something to rotate about a given axis. So in this case I have a top-down view of a door. So the door is kind of connected here at a hinge joint, or that's going to be its axis of rotation. And it means that the rate at which this door will tend to, or the magnitude with which this door will tend to rotate, is going to be dependent on the magnitude of the force and the direction in which that force tends to act, right? So I can have something rotating kind of in this clockwise direction or in this anti-clockwise direction. So that gives us another clue about torque, the fact that it is also a vector, meaning it will also have magnitude and direction. Alright, so there's a couple of things that we would need to unpack here. So torque is denoted by this Greek letter tau. It's kind of like a curly T, if you want to put it that way. So this is the Greek letter tau, which we will use to define torque, which is equal to, and we'll have this letter R multiplied by F. Force is also a vector multiplied by this sine theta. So I'll unpack what I mean by each of these components, but all of this is kind of buried within this definition, right? So there's three concepts in torque or rotational force that are really important. One is the magnitude of force. Two is the distance from the axis of rotation, and three is the direction of force application, right? So all of these are kind of hidden within this, or kind of explained by this particular formula. So let me just for a second unpack each one of them. This here, this R, is also called your moment arm. Okay, and in essence what that is the distance of the force from the axis of rotation, right? So this over here is my axis of rotation in this particular scenario, right? It's the hinge joint of the door, the point around which this door will tend to rotate, right? Okay, so that should hopefully make sense. F over here is the magnitude of the force itself, right? So say for example over here I have a force that I'm applying. This is my force and the magnitude of that force is going to be really important. So let's say for example that was 100 newtons. That will become important just now, and it's going to be acting at some angle theta, right? So that's where the third and final component becomes really important, right? So we say, alright, this over here is the direction component, and this direction component is both going to be affecting this F, or it can affect the length of the lever arm, right? So three really important factors. Let me put in the R. R is something that I'd want to address over here. So we said R is the length or the distance from the axis of rotation where the force tends to act. Okay, so we have our three scenarios over here. Let's just put it into practice. say for example that the length of R was 2 meters. We've already got the magnitude of our force, which is 100 newtons, so F is 100 newtons, and we've got our direction of force application in this case, so theta in this case will make 30 degrees, right? So one more thing that I'd like to unpack is the fact that since force is a vector, the direction is really important. So this force is acting at some angle relative to this axis of rotation, and I can break this force into component parts, right? I have a vertical component and I have a horizontal component. Now, this horizontal component is acting directly towards the axis of rotation and will therefore not cause any rotation. And what you'll notice is it's only this vertical component or the perpendicular component of the force to the axis of rotation that will cause any rotation. So it's only this portion of the force or component of the force that's going to cause this particular door to start rotating, right? Really important aspect to become familiar with. Okay. The reason that is the case, if I just kind of had to redraw that force over here for 1 second, let me just make it a little bit bigger, is if this is my force and this is the angle at which the force tends to act, then I have this horizontal component of the force and I have this vertical component of the force or perpendicular component of the force. So this would be my Fx and this would be my Fy. And what we already know is that Fy from trigonometry is equal to F sine theta, and Fx is equal to F cosine theta. Right, it's only this F sine component that's going to cause any rotation in this particular scenario. Right. Okay, so let's say what is the torque that I would create about this axis of rotation if I was applying this force at some angle. So this 100 newtons of force at an angle of 30. So the torque that I would be exerting is equal to this R component, 2 meters, times this 100 newtons times the sine of 30 degrees, or it's a component of the force acting perpendicular to the axis of rotation. So this would be 2 times 100 times the sine of 30 is 50 newtons, which would give me 100 newton meters of torque. Right, that's just the size of the torque that I would be able to create given this particular scenario. Okay. There's another aspect that just kind of changes the mathematics, which is kind of what I tend to look at, and that's manipulating the size of this lever arm. Remember, it is the component or the distance of the force from the axis of rotation. So you will notice that the bigger R is, the greater the torque is, or the further the force acts from the axis of rotation, right, the bigger the torque is. And also, the more the force acts at a perpendicular angle to the axis of rotation, the greater this force would be. So torque is maximized when both these aspects are perpendicular, right? So if I was playing around with the lever arm length, there are 3 factors that I have to take into consideration, right, to find the length of the lever arm. Remember, the length of the lever arm is not the length of the door, right? That's a really important aspect to take into consideration. So what you do to find the length of the lever arm, if I kind of had to redraw this door, I'll just kind of redraw it over here. So let's say, oopsie daisy, let's change the color a bit over here. Alright, so let's say this was my door and everything else is exactly the same. Right, all I'm trying to do is change the length of the lever arm. So here's my axis of rotation again, and I'm still applying a force at the same angle, right? So this is still the same. Here's still my force component, and this angle component is still the same. Okay, so what do I have to do to find the effective length of the lever arm? Well, step number one is to project the force further, right? So extend the force further in either direction, So in essence what that means is just the following. So I kind of extend this further over here, and I extend it further down here. The second step is to find the shortest distance between the force and axis of rotation, between F and axis of rotation, right? Remember that this over here is my axis of rotation, it's the hinge joint. So the shortest distance between here and this force component. So you'll notice that if I project this further, that's quite a long distance. If I go along the length of the door, that's going to be shorter. But what you'll find is that the shortest distance between the axis of rotation tends to be a perpendicular component, right? So let me just kind of see if I can move this over here. I'm just going to move this down a little bit. Hopefully this works. Alright, so I'm just going to give me a little bit more space over here. Okay, good. So if I just wanted to project this a little bit longer, so let me just take this force component and project it a little bit longer. So what you'll find is, as I was trying to say, the shortest distance between the axis of rotation and this kind of elongated force component is the component that's perpendicular, right? So when this new length, this length of the lever arm, that is perpendicular to this force component, this is my lever arm length, right? Like I said, it's not the length of the door. This is the component of R that is responsible for creating torque, right? So 3, that is going to be my effective lever arm. Okay, so what we've already established is that this is R, so the distance or length from the axis of rotation to force application is R. Okay, well, since this is my angle of force application, the effective lever arm length is this length over here. So this is in effect a right angled triangle. Since R is the component opposite this 90-degree angle sine, this is my hypotenuse. So in essence, that's my hypotenuse. This is the side opposite the angle, and in essence this becomes R sine theta, right? So the length of my lever arm is going to be shorter than this length of R over here because this force is being applied at an angle. So to rewrite that torque formula, in essence it's going to look pretty much the same as this, except where the sign tends to act is slightly different. So now it's going to be the magnitude of the force, which in this case is still 100 newtons, right? But I'm multiplying it by the lever arm length, which is this R sine theta, right? So in this case, if I had to run this calculation again, this now becomes 100 newtons times R is still 2 meters, 2 times sine of 30 degrees, right? So this then becomes 100, and 2 times sine of 30, sine of 30 is a half, so 2 times a half is 1, and I still get 100 Newton meters. Notice how this is exactly the same as this, it's just how I am defining the torque is slightly different, right? So a generalization of torque is equal to force times lever arm. Okay, so what is the component of force that is acting perpendicular to the axis of rotation, and what's the length of the lever arm that is responsible for causing rotation, right? In this instance, this lever arm length is saying that it would be the exact same torque value that I would get if I were to apply a perpendicular force of 100 newtons, a distance of 1 meter from the axis of rotation, right? So that would give me the exact same torque as I would applying a force of 100 newtons at some angle, some distance r from the axis of rotation. So if this force is 100 newtons and it's acting at 30 degrees 2 meters from the axis of rotation, it's the same as if I were to apply a force of 100 newtons 1 meter from the axis of rotation. I would get the exact same torque value, right? So this is inefficient. How could I maximize this torque? Well, I would have to change this angle, and instead of it being 30 degrees, I would want to make that same 100 newtons of force perpendicular, right? If I had to do this, sorry about that, if I had to do this and apply the 100 newtons 2 meters from the axis of rotation, then the torque here would be 100 times 2 meters times the sine, since all of it is perpendicular, it's 90 degrees, and that would give me 200 Newton meters, right? I'd be twice as effective in my torque as I was in these scenarios, right? So that's something to keep into consideration, or keep in mind, that torque is equal to lever arm length times force times the angle of application, and it is maximized when this angle is perpendicular, right? Don't forget that. And that's it. That's a basic introduction to torque, the ability of force to cause rotation, and like we said, it is a vector quantity, so torque has directional application, which is really important, right? So the way in which it tends to rotate is it can rotate anti-clockwise or can rotate clockwise, depending on the direction in which the force tends to act. So again, we ascribe positive and negative values to that. So something that we've established is that when something tends to rotate in a clockwise direction, it is ascribed a negative value, and when something tends to rotate in an anti-clockwise direction, it is ascribed a positive value. So when I do all these calculations and torque ends up being negative, it means something must be rotating clockwise. If I do these calculations and I end up with a positive values, it means something must be rotating, or the object must be rotating in an anti-clockwise direction. Okay, I hope that has made sense. I know it's a lot to wrap your head around. Torque tends to be confusing from that point of view. Just remember or bear in mind that it's the component of force that acts perpendicular, and it's the component of the lever arm that's perpendicular to the force that will define the magnitude and direction of torque. Alright, I hope you've enjoyed that. We'll unpack a couple of examples in subsequent videos, so stay tuned.